Here we go. Reflection and interference and stuff like that. Waves interact with stuff, right? It's transfers of energy. That energy interacts with stuff. And there's a couple different rules and how these waves they react with things. But before we need to know what they react with, we need to define what a boundary is, okay? And a boundary is just a separation between two different waves. I've got a string here and I've got my Apple Pencil. Between them, there is my boundary between the two mediums. I've got string and I've got a pencil. Obviously, a wave in a string is going to move differently than a wave will move in a solid Apple Pencil, okay? That's a boundary. There's two types of boundaries, okay? There's a hard boundary and there's a soft boundary. A hard boundary is something that's rigid or it's a tied end. Like a wall, like a post, anything, but it's a tied end. It does not move, okay? This thing does not move, hence hard boundary, okay? A soft boundary, well, it's loosey-goosey. It's free to move however you want. It just kind of goes with the wave. It's loosey-goosey and it moves freely, okay? For example, wrap my hand around this side, send a wave through. My hand is acting as a hard boundary because my hand is not moving. This string is tied over here, and I've just got a wave going in and out. That's a hard boundary. If I just kind of let this end hang loose and I send a wave through, okay, this is kind of a terrible example, but this end is loose now, loosey-goosey. This is a soft boundary, and that affects how the wave, what happens, the reflection on transmission. So we're going to look at reflection first, okay? Because when something hits a wall, it is going to, if something hits a wall, then it is going to reflect back. If you throw a ball at the wall, that ball is going to bounce back, okay? Now, a hard boundary makes sense because a hard boundary is a tied end, but soft boundaries, yeah, they're weird. It's like, well, what's the point? But what can happen, and I should have grabbed another piece of string. I don't have one. But let's just say I'm going to fake this, okay? Let's say you tie two pieces of rope together, okay? Here's a thick piece of rope, and there's a thin piece of rope, okay? That right there is a type of boundary, right, between two different ropes. It will act as either a hard or soft boundary based on the types of rope. So it's not, like a soft boundary is not necessarily something that kind of like that's just loosey-goosey. Imagine if this rope was so heavy that when I sent a wave through, it could move my hand up and down. That's kind of what a soft boundary is, okay? So when it hits a hard boundary, it reflects with the opposite polarity, okay? It's upside down, okay? This is the upside down. 10 points to Gryffindor if you get that reference. Canceled, they had to stop filming. The new season's not going to come out until next year. It's supposed to come out in like last year came out July 1st. Not supposed to come out until next year. Just want to watch it. Stranger Things, by the way, great show, Netflix, watch it. When it hits a hard boundary, okay, it goes to the upside down. And it goes back the same direction, but it's upside down. It's the opposite polarity, okay? When it has a soft boundary, it reflects with the same polarity, okay? It's just normal stuff, okay? So you've got a hard boundary is like a wall and it goes right back. A soft boundary, it comes back just the way it is. You could probably, if you have a slinky at home or a spring or something, or even just a long piece of rope, you could do this with your family members, get some people to hold something and send waves through, and you can kind of do this. We would do this in class, but it's kind of hard to do over Zoom. Now, with these reflected waves, I messed up here. I didn't realize that. The reflected waves, okay, have the same wavelength and speed as the incident wave. The incident wave, right? This is just the first incoming wave. That's incident wave. So your first wave goes in, the reflected one has the same wavelength and speed as the incident, okay? They're exactly the same. But the amplitude, how big that wave is smaller because you can't, some of the energy gets transferred through, not all the energy comes back. So you might have a wave coming back like this, but these ones might be only like that big, okay? A smaller amplitude, and that depends on on what type of boundary it is, okay? And when I say polarity, this polarity just means it's either up or down, okay? The up is one polarity, down the other one, okay? So one is up, one is the normal way, one is upside down, okay? So hard and soft boundaries, that's how things reflect, okay? But we are going to have transmission through the boundaries, okay? It's just a natural thing that's gonna happen. When you throw a ball at the wall, some of that ball's energy goes into the wall. You can't really see it, but it definitely goes into the wall, okay? If you throw a ball at a net or kick a ball into a soccer net, okay? Some of that ball's energy pushes the net back. That's more of a soft boundary, okay? So same things are gonna happen with waves. And this is where we get wave transmission. And this is just kind of a set of rules, to be honest, that you're just gonna know. You don't have to memorize it because you don't have a written in-person exam, but you do need to know these rules. So when there's three things that happen, okay? You got a wave traveling through a medium, and it hits a boundary and goes into a different medium, okay? Your wave is going to transmit. So coming from the string to the Apple Pencil, some of this wave in the string is going to transmit to the Apple Pencil. Some of it is going to get reflected back into the string, and some of the properties are going to change based on the differences in the mediums, okay? So you've got a transmitted wave, you've got a reflected wave, and you've got different properties. So if you go from less dense to more dense, okay? Less dense to more dense, you might be thinking, well, what the heck does that mean? Okay, less dense to more dense, think of that as, say, going for a walk, say, in a park, then into downtown, okay? Less dense in a park, more dense downtown, right? You can run forever if you're in a park because there's nothing stopping you except for some trees. You don't want to hit the trees. But people wise, right? There's nobody in the park, so you can run forever or walk forever. But downtown, there's people everywhere. It's a lot harder. You probably can't walk or run as fast downtown, okay? Less dense to more dense, okay? So in a string, that would be like, say, fishing, like if I had some fishing line or maybe some fishing line tied to this rope, well, then that is a less dense medium, a fishing line going to a thicker rope, more dense, okay? So what happens? Well, if we think about our running or walking example, okay, can you run faster in a wide open field or in downtown Winnipeg after a Jets game? Okay, probably in the field, which means when you transition and transmit into a more dense medium, your speed is going to decrease. It's going to go down. Okay, the frequency, how often the waves come, that's a property of what's creating the waves, right? So that is going to stay exactly the same because where the waves come from, it doesn't matter. Okay, but where the waves go, that's going to change, but the actual source of the waves isn't going to change, okay? The wavelength, if we use those two properties, we think about the formula V equals frequency times lambda. If the frequency is staying the same and my speed decreases, that tells me that my wavelength must also get smaller, must also decrease when it goes into the more dense medium, okay? And the reflection, just like we talked about, the reflection it's inverted or it's upside down, okay? Because what happens is this acts like a hard boundary, because you've got a small rope going to a thick rope. So that small rope can't move the thick rope very much, so it acts like a hard boundary. So it gets reflected upside down, just like we had up here, okay? Just like we had there. So a picture of this, we are gonna get a small little wave. I'll send in a wave pulse like that, okay? Let's say this wave is going like so. Then it is going to hit a more dense medium. And what's going to happen? The wavelength gets smaller, and the speed decreases. So this thing is going to go like, maybe like that, right? See how this wavelength here, if this was say 1, then this is say 0.5, okay? It's smaller, okay? And this thing is moving, I don't like how thick that is. This thing is moving slow, and this is moving fast. The only thing that's left is the reflected wave, and this thing gets reflected upside down with exactly the same wavelength, maybe smaller amplitude, because right, this one wave here made 2 waves here. So they can't both have the same amplitude, but it's the speed and the wavelength that changes, okay? That's what's happening here. Amplitude, remember, characteristic from last lesson, how big the wave is, okay? How big the wave is from the middle point up to the top. That's from the last lesson. So now if we do the opposite and we go from more dense to less dense, that's like starting your run in downtown Winnipeg after a Jets game and then going to a wide open field. You might be really slow at the start, but as soon as you break away from the crowd, now you can run all you want and you can run faster, okay? Which means the speed is going to increase. Frequency still stays the same. You're not changing how fast your legs are moving, right? There's just nothing in your way. And the wavelength, again, following the same pattern of B equals frequency times lambda, right? Well, if the frequency or if the speed increases, that means that the wavelength must also increase. Wavelength is longer. And the partial reflection is the same as the start, as the incident wave. Okay? Because this one acts like a soft boundary, because you've got a more dense medium controlling the less dense one, so it can just do what it wants. It moves that small one, okay? And a picture of this, here we go. Here we have our wave going in like this, like that. We've got our wave traveling like that. We'll say that thing is, actually, I won't add that quite yet. But then it goes into a less dense medium, a skinny one. The wavelength is going to increase, make that much, much longer, like so. And the partial reflection through this wave is the same as it was. Same wavelength moving this way. Same wavelength, same speed. And over here, right, if it starts off slow, now it's going to go super fast. Okay, and these are all relations to each other, right? So if this is, right, if this starts out with a velocity of say 2 meters per second and a wavelength of 1 meter, well, if this wavelength now becomes 2 meters, well, then that means that this velocity is going to be 4 meters per second, right? They're proportional to each other. If one increases by a factor of 2, the other has to increase by a factor of 2. Okay, now I can show you some fun little pictures of this. okay? So this is less dense to more dense, right? This is what we just drew, okay? Less dense to more dense. You have your incident one going in, you have a smaller wavelength in the more dense one, and you've got a reflected, inverted, upside down wave pulse, okay? We can look at exactly the same thing, but more dense to less dense, see how we have a longer wavelength and a reflected pulse that is the same polarity, same up as the incident one, as the first one. Now, there's for some reason there's only one GIF of this from less dense to more dense. This is what is happening on this string. And if we were in class, again, we could do this with slinkies and springs, but unfortunately, we don't have that. You've got a less dense medium on the left here, send a wave pulse through. Notice how, first of all, the reflection is upside down, going at the same speed on the way back. But in the more dense medium, notice how the wavelengths get shorter and the pulse goes much, much slower, okay? The amplitude is also smaller. The wave is not as tall, okay? This is what's happening. This is what we're talking about. So we can do some math with this. We can actually compare different mediums and look at how the velocity and the wavelength changes, okay? So we're just gonna do this one example. I don't wanna do the other one. You can do it if you want. I'll fill in the notes. We're just gonna do this one, okay? So we've got a triangular wave pulse that's going through three different mediums A, B, and C. So three different types of materials, say three different types of string. Say fishing line, thick rope, and shoelace. Sure, okay, three different ropes. It tells us that the speeds are 1 meter per second, 2 meters per second, and 1.5 meters per second. So let's go ahead and throw that on here. We're gonna get the velocity in A is 1 meter per second, the velocity in B is 2 meters per second, and the velocity in C is 1.5 meters per second, okay? So right away, since the wave is traveling faster in B, that's telling me that that is a less dense medium because the wave is going much faster, okay? We want to figure out, complete the diagram, we want to figure out what the wavelength is, approximate amplitude and wave direction, and if it's inverted or not, okay? So this right here says that A is more dense than B, okay? More dense than B. So if the velocity of B is twice that of velocity of A, then that's going to tell me that the wavelength of B is also going to be twice that the wavelength of A, because they're exactly the same thing. And since we use the formula, velocity equals the frequency times the wavelength. Because remember, the frequency here doesn't change. Frequency doesn't change, okay? So we could go ahead and draw that picture, right? We can just say, well, we've got a longer wavelength going into B like that, and this thing is moving like so. If this here is X, then this is 2X. It's twice as fast, okay? More dense to less dense means it acts like a soft boundary, okay? So this right here is soft, which tells me that the reflected one is going back same wavelength, same speed, but moving in the opposite way, okay? Cool. Makes sense. Now we can do the same thing with C, okay? We can say, since this speed is decreasing, we can say that C is more dense than B, okay? C is more dense than B, which means this is going to act like a hard boundary right there, okay? And if it's acting like a hard boundary, okay, our reflected wave, we could do that first if we wanted, our reflected wave is gonna be upside down. It's gonna go like that, upside down. There's a reflected wave. I think my screen is frozen. There we go. So C is more dense than B, and our reflected wave right here, oops, I didn't want to erase it. Our reflected wave right here is going in the opposite direction, upside down, because it's more dense to less dense, or sorry, less dense to more dense. It's a hard boundary, okay? Now our wavelengths, right? What the heck's happening here? Well, if we follow the same thought process as the last one, right? Our velocity, it's 1.5 times, right? Which means the wavelength of C is going to be 1.5 times the wavelength of the first one, which is we just called it X. So this thing is going to have a wavelength, not quite the full, to a little bit more than A, but less than B. Okay, and we could say, right, since it's moving faster in C compared to A, we could say that C is also less dense than A. Okay, this is sort of weird. Like, this is a weird question, I'm not gonna lie. I always kind of question if we should actually do it or not. But this is kind of how the math works with this. The frequency is always going to stay the same, and you can change up the wavelengths and the speeds based on what's happening. Okay. Question number 2, we're not going to do it. We're just going to skip it. I don't feel like doing it. It's the last day of class. Okay. You can do it if you want. The answer is 1.1 centimeters. Okay. So if you can get there, great. I'm not even going to post it. It's totally fine. It's whatever. Because I want to take 5 minutes and I want to talk about superposition of waves first, because this is more fun. Okay, this is interference and the principle of superposition. This is just a fancy way of saying how do waves add or subtract together. Okay, if you have 2 different waves acting on the same particle, that particle is going to be conflicted, right? You don't know what it wants to do. Does it want to go up? Does it want to go down? Does it want to go really up? Like, what does it want to do? These things just add together, and you get constructive interference and you get destructive interference. Those words are very, very easy to understand. Constructive means you're building on something. So when you have 2 waves that come together, they add together to make a bigger wave, and you just add them together. So if you've got 2 waves that have wavelengths of X and X, when they meet together, they make a wavelength of 2X, but then the waves keep going and pass each other, and then they continue on as their normal waves. So you've got waves coming in like this, they meet, they make a big wave, and then they keep on going like that. Okay? That's because they're both going in the same direction, right? Those wave pulses are both up. So they add together, okay? But destructive interference is exactly the opposite. They destroy each other to make either a smaller wave or no wave at all if they're perfectly equal. So exactly the same idea. We have X, but negative X because we've got opposite waves. So when they meet each other, you get nothing, but then the waves keep on carrying through, right? You've got waves going like this, and then when they meet each other, they're both going to be doing like this. It's kind of like a free body diagram, 5 up, 5 down. So you get nothing in the middle, and then those waves keep on going, right? Without one thing, this wave would go like this. Without the other wave, this wave would go like this. When they go together, right, they destroy each other in the middle, and then they keep on going. Destructive and constructive interference. Okay, That's it. That's it. It's super cool. I think I have a fun video. Give me 1 second. I think I have to find it. Is this gonna work? Okay. This is my favorite. Actually, I'm gonna stop the share for a second and then I'm going to resume it. Share screen because I want to share. Watch this. This is fantastic. This is an example of superposition of waves in um, in real life. You got a surfer. It's great. Waves on a beach. Boom, boom, ba-doom, boom, boom, ba-doom, boom. Right? Because you got waves coming into the shore, you got waves coming back from the shore, and when they meet each other, they go boom. They make a big, huge wave, send that surfer up in the air. It's fantastic. Isn't that fun? That's so cool. Let's watch it one more time. Just watch this surfer go flying up in the air. It's fantastic. Boom, and then boom, there he goes. He was okay, by the way. But that is what type of interference? Constructive or destructive? I don't know. What do you think? Constructive or destructive?
Constructive.
Yay, constructive. Beautiful. Because they add together one more time. Watch this poor soul. Do, 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 do. He looks so happy. Great wave. And then boom, destroyed. Okay, that's enough of that. Fantastic. Yeah, okay. Now, there is a question on Quest that looks very similar to this if you've looked at the Quest, okay? I'm not going to ask you this question ever again except for this one time, okay? So I'm going to kind of walk you through how to do it, okay? Now, you've got two waves that are moving towards each other. On this side, this is wave number one, okay? And over here, this is wave number two, okay? And so just to clarify, this is a Quest question, okay? Both waves are moving towards each other with velocities or with speeds of 1 meter per second, okay? And we want to know what the shape of the wave is after 2 seconds, okay? Now, we can kind of do this two different ways. First, we look at the blue wave, okay? And the easiest way to look at this is just to go point by point, okay? This blue wave here, I'm going to erase the highlights just so it's not as messy, right? At 0, okay, this wave has 0 amplitude. But in 2 seconds, this thing is going to move 1, 2, and it's going to go right there. This is the new start of the wave, okay? At 1 second, we move it forward 1, 2, it goes right there, right? So this thing goes like this. I'll make this a little bit thicker so we can see this. This wave goes over, and then it goes up like that. We are just taking this entire wave and we are shifting it over to the right too. Now, I'm going to cheat a little bit, and I'm just going to do this. Instead of tracing out every single point, I'm going to trace my wave like that. And then because I can do this, I'm going to take this wave, I'm going to move it over 1 second, 2 seconds. There's my new wave, moved over to the right, okay? And I can do exactly the same thing, but with this second wave that goes up like this. But this time, right, this wave is going to the right. So I'm going to take this purple wave and I'm going to move it 1 second, 2 seconds over to the left, okay? And now what we're looking at is how do these two waves add or subtract together when they meet each other, okay? And what you can look at for there is I like just picking points for it. Now, I'm not gonna lie, your Quest question is multiple choice, so use that to your advantage. Pick a point, pick a specific point and stare at that, okay? At, let's say 5 seconds, okay? Let's look at 5 seconds. at 5 seconds, the blue wave is equal to 0, the purple wave is equal to 1, which means the total wave must equal 1, okay? So we know at 5 seconds on our combined graph, we are gonna get a point right there, okay? And you can just go point by point, okay? Let's look at, say, 6 seconds right here, okay? At 6 seconds, we have the blue wave equaling minus 1.5. The purple red also equals minus 1.5. So together, the red wave is minus 3. So now this thing goes from here to here. Okay, so this wave, there's part of our wave. Okay, and for this quest question, and I'm showing you just for this quest question, you don't need to actually draw the wave. You can use process of elimination because some of the waves might have this property, some of them won't, and you can just eliminate them. Okay. Try this question. It's a little funky. Try it exactly how I did it. Move your waves over, look at the point, see how they add and subtract, and you can start to kind of build your wave like this. I'll do one more at 4 seconds, right? At 4 seconds, we've got 0 and 1, which means we are also going to be at 1, right? Like that. And then you just keep doing it, right? At 3, we have -1 and 0. So we're at -1 there. At 2, we just have, from 3 on, we just have the blue wave. So we go up like this, like so, right? And then we keep on going and going and going. Okay, I might as well finish it. I'm right here. At 7, we have 0 and 1. So we're up at 1. We go up to there. And then now we are just the purple wave going down to 0. And that right there is our combined wave right out after 2 seconds. Kind of fun. Kind of fun. Okay. Again, I'm only asking you this question once on your waves quest. So try it out, see what you can do. You don't need to draw the full wave, just kind of process of elimination. Okay. And you know what? That's enough for that. I don't really want to talk anymore. Do you want me to keep teaching? First person to respond. Do you want me to keep teaching, or should we call her a course? Call her a year? No. Okay, done. No more teaching. That's it. We done. Okay. Hopefully this didn't confuse you too much today. Kind of, there's two different things, right? There's a superposition of adding waves together, right? Either they add together or they cancel each other out. And then there's these hard and soft boundaries with different mediums. Really, this right here, this is the important stuff, right? Knowing those rules, and you can deal with anything. Okay, but just think about running in downtown Winnipeg versus running in an open field. Okay, and vice versa. How does things change? Okay, and that is it. Yay! We did it. How do I stop? No, stop the share. That's not what I wanted to do. I wanted to stop